So in this last video, we'll be talking about Le Chatelier's principle. And at the end of this video, the students or you should be able to first define Le Chatelier's principle, and second, to use the principle to predict how change in concentration, pressure or volume, and temperature affect systems in equilibrium. Okay, so um, So defining Le Chatelier's principle is named in honor of Henry Louis Le Chatelier. Some sources would pronounce his last name differently. Okay. And then his principle simply states that when you have a chemical reaction which is already at equilibrium and it is disturbed, okay, then the system will find a way on how to relieve that stress or how to re-establish equilibrium. So this concept is not very far from what you've learned in your biology, wherein an organism will find a way to achieve homeostasis. So what are the disturbances that could happen in a system already at equilibrium? So these disturbances can be in the form of change in pressure, change in temperature, or change in component concentration. So to illustrate the point, let's look at a system at equilibrium. So when you have a system at equilibrium, it means that our Q is already equal to K, right? And then I'm showing here a seesaw as an illustration. So I have to point out, okay, that the amounts are not equal. You have to recall that a system at equilibrium does not mean that the amount of reactants and products are equal. It simply means that the rates of forward and backward reactions are equal. But this would be helpful as an analogy later. So let's say the system is already balanced or at equilibrium. And then we introduce a particular stress. For example, we try to increase reactant concentration. So now our seesaw wouldn't be balanced. Since we are increasing the amount of the reactant, the left side will be heavier. Okay? And what would the system try to do for it to go back to its equilibrium state? Okay? So you might think, well, we could move or transform some of the reactants into products so that we could re-establish equilibrium. Okay, so again, when we increase the reactant concentration, what would be its effect? Okay, the effect would be the equilibrium, okay, or the system tries to shift the equilibrium to the right, meaning some of the excess reactants would be transformed or converted into product for it to re-establish equilibrium. Okay. In the same manner, when we increase product concentration, okay, that means the right side becomes heavier. And can you guess what the system will do to establish equilibrium again? Okay. So the equilibrium now, once the products are much bigger, you increase the product concentration, the equilibrium now shifts to the opposite direction, to the left side this time, for it to reestablish equilibrium. Okay. Similarly, okay, so that's for increasing reactant or product concentration. But what if we try to remove, okay, we try to remove a reactant or a product. So let's say the stress we are introducing is a decrease in reactant concentration. So when we decrease reactant concentration, still we'd have this illustration. The left side will be much lighter. Okay, just like a C, so how can we balance this again? Okay, so to do that, the equilibrium will shift to the left to re-establish equilibrium. So, how can we decrease reactant concentration in actual reactions? So it's not just simply trying to scoop out the reactants out of the vessel, okay? Just like what you have observed in your experiment in shifting equilibrium, if you can recall, you you added silver nitrate to the system, okay? You added silver nitrate, the reagent in the amber or brown colored glass, and once you added that to your mixture, you found that there were white precipitates. Some of you exclaimed that the it's a foggy pink color. Okay, so the addition of silver nitrate to the system actually decreased the amount of one reactant. So the silver ion captured the chloride ion in your mixture and transformed it into a precipitate. And that's what the white precipitate, which caused the mixture to become foggy. So that's actually an example of decreasing reactant concentration. So we're forcing out one reactant to be removed into the mixture. Okay, so next, we go in, let's try to summarize changing component concentration. So when we increase a component concentration, either reactant or product, then its effect would be shifting the equilibrium to the opposite side to reduce the added component. Second, when we try to decrease a component concentration, the equilibrium shifts to the same side where there was a decrease in amount for it to replace the component removed. And it's very important to highlight that when we change a concentration of our component, that does not change equilibrium constant. Okay, now let's go into the effect of volume and pressure changes in the system. So let's take, for example, a reversible reaction of A and B forming together to form C. And we have this illustration here. Okay, so let's say the system is at equilibrium. And then what happens when there's a decrease in volume, or since you already have your ideal gas law or uh, lesson about gases, you understand that decrease in volume is or can be attributed to an increase in pressure as well. So these two changes can be the same or have the same effect. So it was found that when you have a reversible reaction at equilibrium and we decrease the volume or increase the pressure, the system would shift, okay, the equilibrium would shift in the direction to the side with less gases. So in this illustration here, in this sample reaction, the left side, okay, which you have to remind yourself that change in volume or pressure is only applicable or would only affect gaseous components. So the left side has 1 plus 2, so you have 3 moles of gases in total. Whereas the right component or the right side, product side, has just one gas molecule. So the reactant side has more gases and the product side has less gases. So when you decrease the volume, So a decrease in volume or increase in pressure would shift the equilibrium to the side with less gases, which is in the product side. Okay. And then if we do the opposite, we try to increase the volume or decrease the pressure, then the equilibrium will shift to the side with more gases. Okay? So you just try to remember that it would seem like when we make the space for the gases more cramped, they would find a way to make it less cramped. So they will find a side or they will favor the side with less gases. Okay? Then if you have bigger space for the gases, they would want to fill it up again to reestablish the total pressure. So they would favor the side with more gases when you have greater or bigger space. Okay, so to summarize, okay, the volume and pressure changes only affect systems in equilibrium with gas components, and then reducing the volume or increasing the pressure of the mixture will shift equilibrium to the side with less gases, and doing the opposite would shift equilibrium to the direction with more gases. Also, it's important to note that when we try to increase the pressure, not just by changing the volume, okay, when we try to increase the pressure by adding an inert gas or a non-reactive gas to the mixture, a gas that is not part of the reaction, the equilibrium will not shift to any side. So it will just stay as it is. And changing the volume or pressure does not change the equilibrium constant. Next, we move to the effect of temperature changes. Okay, so you have to recall the terms endothermic and exothermic. So endothermic is the addition of heat. Okay, the reaction absorbs heat, and exothermic reactions are those that release heat. And you have to, when we study temperature changes, you have to treat heat as a sort of a component, sort of a reactant component or product component, chemical component. Okay, for endothermic reaction, when we increase the temperature, okay, I hope you can visualize that. When you increase the temperature, this side here becomes heavier. Okay, so that would tilt the seesaw, which makes this heavier. And when that happens, the equilibrium, just like when we're doing concentration changes, the equilibrium will shift to the right to produce more product. Okay? And also, increasing temperature of an endothermic reaction results in a higher equilibrium constant. Conversely, for exothermic reactions, wherein heat is sort of part of a product, increasing the temperature, okay, would make the right side sort of heavier. And this would shift equilibrium to the left or to the reactant side. Also, increasing temperature of an exothermic reaction results in a lower equilibrium constant. Next, effect of a catalyst. So, in our chemical kinetics lesson, we have discussed that a catalyst, it speeds up a reaction by finding an alternative pathway. So the one in the blue curve. So this is for the uncatalyzed, the red one. And the blue curve is for the catalyzed reaction. However, as you can observe here, the catalyst only changes the reaction in a sense that it makes the rate of the forward faster and the rate of the reverse faster. In fact, a catalyst will not change the equilibrium position. Okay. So let's try the sample problem. So consider the equilibrium reaction of dinitrogen tetroxide in equilibrium with 2 moles of nitrogen dioxide. We're given the standard enthalpy here. Okay, so recall that enthalpy would tell you the energy change of a reaction. We're asked in what direction the equilibrium will shift when we add more reactant. So if we add more reactant, then the equilibrium shifts to the right, okay, to the opposite side. Next, B. What if we remove a product? So this side, the product side would be lighter. When that happens, the equilibrium will shift or try to make more of those removed components. So the equilibrium shifts to the right still. Third, the total pressure is increased, okay? So total pressure is increased, meaning we could be making the volume smaller. So since it's more cramped, the system will favor the side with less gases. So we have less gas in the reactant side, right? You have only 1 mole of gas here, you have 2 moles of gas here. So the equilibrium shifts to the left or to the side with less gas. Next, D. What if the volume is increased? Okay, so this is the volume is increased, so there's more space, and now the equilibrium will favor the side with more gases. You have equilibrium shifts to the right. Fifth, the temperature is decreased. Okay, so we have to look at the enthalpy. So the enthalpy is a positive value here. So a positive delta H means that this reaction is endothermic. Again, a positive delta H means the reaction is endothermic, meaning the reaction will try to absorb heat. Okay, so the heat is at the reactant side. If we decrease temperature, that means reactant side will sort of become lighter, and to compensate, the equilibrium will shift to the left. And then lastly, letter F, okay, what if we change the total pressure, we increase it by the addition of N2, okay? Now N2 is not a chemical component, so N2 is an inert gas in this case, and inert gases does not shift the equilibrium position. I hope that helps.